right, hi everyone. Here we are today. We're going to discuss Weinberg. So for those of you who are not big fans of math, you might have cringed at the thought of doing yet another bit of math in bio class. So what I want to do is kind of take the math out of the equation for a minute and just look at how Hardy-Weinberg works, and then we'll do a couple of problems or do an example, and we'll bring the math back in and see what you guys think about it. So again, Hardy-Weinberg. Now, Hardy-Weinberg, really, when you're at a Hardy-Weinberg equilibrium, these are when you have a very large population, so large population size, no mutations. So when you say no mutations, that means no DNA mutations, no mutations caused by external conditions, none of that. No gene flow. Remember, gene flow is introducing new alleles into the population. All right? Random mating. That means you're not going to choose your mate, but it's assigned to you. So it's almost like, imagine, everybody, there's 100 people in a room, 50 male, 50 female, everybody gets a number, and you're told that you have to mate with number 5. So that's completely random, all right? That means you didn't choose that individual based on how they looked or based on the fact that you like them because they had, certain characteristics. The last one is no natural selection. All individuals survive and reproduce. So in a real world situation, not all individuals survive and not all individuals reproduce. But to be at a Hardy-Weinberg equilibrium, you have to have all these conditions to be at equilibrium. Now, for this you want to be able to control the alleles. We don't want to introduce new alleles, and basically the alleles should stay constant within each generation. So let's take a look. So, all right, so let's look at an example. Let's look at the gene head shape, and it's just some arbitrary silliness. And our alleles are going to be round and square. So you can either have a round head or you can have a square head. All right. So let's take a look at genotype. In our population, I'm going to use the letter H. If you have the genotype HH, so you're homozygous dominant, or you're heterozygous for it, you're going to have around your phenotype. Will be a round head. Okay? If your genotype is little h, so you're homozygous recessive, your phenotype will be square head. All right. So now let's do an example. All right, so what I want to do is kind of model. I physically want you to see the genotype of 50 individuals. All right, so what I'm going to do in order to get these genotypes, I have a penny, or 2 pennies, and what I'm going to do is I'm going to toss them. If I get heads, heads is going to be the big H allele, and tails is going to be little h. So we're going to do the genotype for person number 1. I got 2 on tails. All right, let's flip it again. 2 on heads. what I'm going to do is I'm going to skip ahead and I'm going to go ahead and flip this 50 times so that we get an entire population. And then I'll be back. Okay, so now I'm finished. So I flipped the coin. Again, I flipped the pennies 50 times and then would get the genotype. So again, I got this one's heads and then tails. So if you get one heads, that's H. If you get a tails, it's little h. So here are all the genotypes that I got after flipping the pennies 50 times. So what I want to do now is kind of do a tally to see how many we have of each. So our 3 different genotypes are homozygous dominant, heterozygous, and then homozygous recessive. So let's count. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now you're probably thinking, why did she do those? Well, what I noticed when I was doing my flipping is that I was getting mostly heterozygous. So I figured if I counted up all the homozygous recessive ones and then the homozygous dominant ones, I could figure out. So let's clear my calculator. I'm going to do 11 plus 9. So 20 individuals. So 30, if I were to go through and count, would be heterozygous. So let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. Yep, so we have 30. So this is all, this is our information. So what does this mean in the grand scheme of things? So if I could look at my population and I could look at everybody in my population and I could see their genotype, this is what I would see. But remember, we don't see genotype, we see phenotype. So what we would really see is so this one's 11 plus 30, so that's 41, right? 41 people would look like this. And 9 people would look like this. Right? That's what we would see. This is how we start Hardy-Weinberg. Most of Hardy-Weinberg, we don't know if it's homozygous dominant or heterozygous. So when we see this person, we don't know if they're homozygous dominant or heterozygous, right? But when we see this person, we know that they are homozygous recessive, okay? So keep that in mind. We're going to put this to the side for a second. Hardy-Weinberg's equation, there's 2 we're going to look at. There is p squared plus 2pq plus q squared is equal to 1. Now, what the heck does that mean? You're probably thinking, okay, here she goes. She started the math part. What does that mean? All right, p squared. Let me just give you an idea. P squared is going to be that homozygous dominant genotype. 2pq is going to be your heterozygous. Remember, we always write it like this, but you very well could have this, right? That's where the 2 comes from. So you have 2 different forms. And then q is going to be little h, little h. That's what it means. Now, we have one more equation. P plus Q is equal to 1. All right, so let's find the allele frequencies in our population. Again, let's start with Q first. Now, what we know is this. Let's go back to our little diagram. We know this, right? So let's pretend that we do not know any of this information here. Okay, I'm going to actually cover it up with a Post-it just so we can't look at it anymore. Doesn't really truly cover it up, but let's pretend it does. All right, what we know is this. We are looking at a population of 50, and we know that 41 of them have a round head and 9 of them have a square head. So let's start. Those 9 we know are homozygous recessive. So let's calculate some allele frequencies. Q squared, remember we said, is going to be little h, right? And we know that 9 of our individuals have a square head. So 9 out of 50 people have a square head, right? So let's go ahead and do that math. And I want to make sure you can see it. So 9 divided by 50. And I'd say it's safe to just go ahead and do everything to 2 decimal places. Go with what your teacher says, but I think it's best to just kind of get in the habit of rounding everything to 2 decimal places and just stay consistent. So we're going to say this is 0.18. All right, we have done most of the work at this point. So we have Q squared. Now, we want to get Q by itself. All right, if we can get Q by itself, so we know Q squared is equal to 0.18. Remember in math, if you want to get rid of a square, you have to do the opposite function, which is take the square root. So what I'm going to do here is take the square root of this side and the square root of this side. So this cancels with this, right? So that leaves us with Q. And then into the calculator, I'm going to do square root of 0.18. And that is 0.42. Now we have, what is this Q? Now up here I wrote allele frequencies, but I didn't really explain, so let me go back and explain. What is an allele frequency? If you kind of want to put it in like a layman's term, or what does it generally mean? Frequency just means how often. So how often are we going to see that Q allele? And here it is. Our Q allele is going to be seen 0.42, which is 42% of the time. All right, so that's our recessive allele. Our recessive allele is going to be 42% of our population. That's basically what this is saying. P, how do I find P? So we have that other equation. P plus Q is equal to 1. We know now that Q is 0.42. We can find P, right? Set this up just like X. Remember in algebra when you're solving for X, it's the same exact thing here. If we want to get P by itself, you subtract by 0.42 from both sides. And I'm going to avoid doing any head math, so I'm going to go ahead and do this math out. And let's type in the right numbers. And everything looks good, 0.58. All right, so what this is telling me, this is the frequency of the dominant allele. So let's translate what this is. That means we're going to see big H 58% of the time. And we're going to see little h 42% of the time. That's what that means. All right, so what is that? Let's take a look at genotypes, though. How often are the genotypes? We already know that Q squared is going to be So let's give us a different piece of paper. We already know that Q squared is 0.18. That means that we're going to have little h 18% of the time. And I'm just multiplying this by 100 to get it into a percent form. Generally speaking though, when you're being asked for a frequency, you give it in a decimal form. You do not put it into a percentage form unless it specifically asks for a percentage. Now, what we want to find here, what is P squared? Remember that is homozygous dominant, right? And then we have that 2PQ, which is heterozygous. Let's find percentages for these. All right, so let's think about how we can do that. On our previous sheet, we said that P is equal to 0.58. Well, to find P squared, it's going to be 0.58 squared. And let's go ahead and see what that is. So that means this will be seen 34% of the time, right? All right, now let's go heterozygous. We have to go back and look, and I need to pull a number from our previous paper, which is Q, which is 0.42. In order to find 2PQ, we're going to have to do 2PQ is going to equal, that's that heterozygous one. We're going to say 2 times our P, which is 0.58. I'm kind of running out of space, times 0.42. And actually, I'm going to bring this down. Let's just do another sheet. Well, we'll just do it here at the bottom. Let's scribble this and just write it here at the bottom. 2PQ. So 2 times P is 0.58 times Q is 0.42. So our 2PQ, and what we're going to do is just put that right in our calculator. 2 times 0.58 times 0.42. And let's double check and make sure I plugged in everything correctly and everything looks good. 0.49. So that means our heterozygous one, oh, why did I write that? Thinking heterozygous and I write something crazy. Heterozygous with the right alleles. Here is going to be 49%. And if we do this math, 18 plus 34 plus 49 should be 100%. And then this is giving us 101%. I would assume due to rounding. Yeah, let's double check. Yeah, it's due to rounding. So we did get something a little bit over 100%, but again, it's due to rounding. So let's go back and look again. Let's scribble out this nonsense we have here. Guess what, guys? You just did Hardy-Weinberg without ever plugging it into the formula, okay? Break the math down into little pieces and think about what you have, all right? So what we had in our population, let me find our little people. We had 41 individuals that had a round head, okay? 11 of them were homozygous dominant, and 30 of them were heterozygous, okay? We had 9 of them that had a square head, or it's more like a rectangle, and that were homozygous recessive. We went through and did the math. Again, we only use recessive information because in our population, remember, we don't see genotypes, we only see phenotypes, and we can physically get the genotype of these guys. So that's what we started our math with. Okay. If we looked at just allele frequencies, this is an allele here. that means 58% of that population, so this population that we're talking about here, 58% of this population is going to have a dominant allele. 42% will have a recessive allele. That's what that means. Okay. Here, 18% of our population will be homozygous recessive. 34% of our population will have homozygous dominant, and 49% of our population is heterozygous. I will do more examples of this, but just to keep this video short, I'm going to end this here. If you have any questions, please leave them in the comments below. Thank you.